Okay, so continuing on with class 3, we're going to talk about this motion relative to a frame in translation, or I just think of it as relative motion. General relative motion in 2 dimensions. We're going to use this concept. It's a good concept alone by itself to understand, especially if you're dealing with like aircraft or ships and things, and you want to see like one thing moving with respect to another thing. You need to be systematic in the way that you approach it so that you can understand. So it can be kind of confusing. So knowing how to do the vector approach on this is really important. So let's see. And maybe I should get rid of the page numbers in these notes right here because this page number probably is to some older version of Beer and Johnston. If we want to find the position of a point, and let's say we know the position of another point B, like we know where B is, and we know where A is with respect to B. Remember, A with respect to B, the B, we say that phrase, A with respect to B. If we know where B is and we know where A is with respect to B, we can find the position of A. And noteworthy that by having Anyway, this is like the main equation for that right here. So this is saying we know B, we can add A with respect to B, so this becomes the reference. We can find the location of A. We could also rearrange this. It makes it a little easier. We see that A with respect to B is equal to A with respect to O minus B with respect to O, right? So we're using O as the reference in both of those, and we can almost think of this as an additional kind of math right here, where this is like we had to have those things true so we could subtract that out. And when we subtracted it out, that says A with respect to B right there. So A with respect to B, A with respect to B, right? In that big idea. And something to keep track. But we normally just ignore that there's an origin somewhere, not just kind of understood. So we just go ahead, instead of saying A with respect to O and B with respect to O, we just say A and B right here. So this is the fundamental position vector equation right there. And we note when we go, if we wanted to use vector triangles for this, that we do this classic thing where we go nose to tail right there, and then the answer is tail to tail, nose to nose. That's at least the way that I remember doing it. And if you want to set up this equation right here where you're adding 2 vectors together, you go that nose to tail from this guy to that guy, and then we go tail, tail, nose, nose, right, on the other side of the equal sign. And the same true, if we took the derivative of this, we would see that they're totally fine to do that, just keeping it as vector symbols right here, that we would get the velocity of A is equal to the velocity of B plus the velocity of A with respect to B, right? So this is like, and this becomes the reference, right? And the same thing true here with the acceleration. We want to find the acceleration. We know the acceleration of B, and we also know the acceleration of A with respect to B, right? And we use this as the reference, and this is the relative motion that's taking place. We're able to find what the acceleration of A is. It's, for instance, if you're this one right here, if you're traveling, and hopefully in the right lane, because you shouldn't be in the left lane, but if you're traveling in the right lane and you're going 60 miles an hour and you see somebody passing you in the left lane and it appears like they're going like 15 miles an hour, right? If you were just standing on the side of the road and you could see somebody driving 15 miles an hour, you might use that as a reference, right? But now you're in a car that's moving 60 miles an hour. You could see that other car going by you, what perceived to be 15 miles an hour, that's its relative motion. So that's like the basic idea that's right here. But we want to make sure that we could do it with triangles. And something to note here is that, like, we could also let's just stick with the velocity on those. If you had instead VB is going to be equal to VA, now use A as the reference, right? You'd actually have VB minus v a with respect to b would be the thing that you would use, right? But if this is the reference, we would rather have it b with respect to a, so it should be vb, excuse me, sorry, it should have vb is going to be equal to va plus vb with respect to a, right? It says with respect to, so that means that is the reference right there, right? So one consequence of that we'll know is that va with respect to b is equal to negative vb with respect to a. So if you just want to, if you're given one and it's actually better for you to have it the other way around with the other one being the reference, just know that you just take the negative of that. And you could prove it with vector triangles if you wanted to, that's going to be the case. So I think this is a short video, right? Let's see. Yeah, it's short enough that I'm going to go ahead and do the example right here in it. Okay, so here's an example. We have two snowboarders traveling down a hill on separate slopes. Newt Dog here, he's at a slope that's 25 degrees, whereas this snowboarder dude, he's at a 10-degree slope. And he's going 10 meters per second, and he's going 14 meters per second, right? So you could do this by way of triangles, you could do by components. I think it's better to do it by way of breaking it into components. So if you break it and you say, let's just take Newt Dog, and we'll say that his velocity here, well, he's going this direction along the slope, right? So he's got an x component and a y component to that. So his x component is going to be 14 times the cosine of 25 I, and plus, but now he's going downward, so I'm going to say minus 14 times the sine of 25 j. And if you were to do that, you would get 12.69 I, and then plus negative 5.917 j. And we might want to say that these are, you can put the units back onto the end of those, right? And then you take VB, you say it's equal to, he's going to be 10 going horizontally in positive, cosine of 10 degrees I, plus, and he's going downwards right there, right? So a negative 10 times the sine of 10 degrees j, meters per second, which if we go ahead and do the math out here, we get 9.848 I plus negative 1.736, so not a lot in the j direction. So what we're trying to find, we want to find the velocity of A with respect to B, right? So we want to find the velocity of A with respect to B, which means we have to take the velocity of A and subtract out the velocity of B, right? And so if we do that, let me just write it out long ways here. We take 12.69, subtract out 9.848 I, plus negative 5.917 minus 1.736 j. And we get VA with respect to B is going to be equal to 2.84. I didn't bother with keeping the fourth sig fig, plus negative 4.18 j, meters per second. Now it's really good to do this as a vector, right, and to test yourself with the vector. I'll use my handy dandy ruler here. And I'll kind of try to sketch the thing out. I might even try to use a little bit of magnitudes right in here, right? So we're saying, this this guy right here, this triangle, will also look like that VA is going to be equal to VB plus VA with respect to B, right? So that's just turning this thing around. It's easy to do the triangles this way. So if you take A, so let's try. Maybe I have this one correct. Maybe that angle is correct. A lot of times I will draw the things correctly. And I'm just going to say, let's see, he's 25. So each of these, I'll go, yeah, each of these is going to be, there you go, right there. There's 25, right? So yeah, 1, 2 and a half, right? So that's 2.5 right there. And let's give him a little arrow there. Okay, so there's our first vector, and what we add, we're going to add this right here. So the answer is going to be A right there, right? So he is just going to be, he's going to be at 10 degrees. Right there. And let's see if I got that right. Here's going to be my vector right there. There's going to be my vector. So this is V of A, and this is, whoops, I think I messed that up. No, that's right. V B. So this is going to be V A with respect to B. I think I got that right. Yep. So there's the triangle math onto the thing. Now what you could do to be able to, or the triangle representation of the thing, what you could do is you could come in here and start figuring out that right there is going to say that's going to be 10 degrees. Doesn't really look like 10 degrees, does it? Looks pretty small. This right here is 25 degrees right in there. And then you could get what the known magnitude of this is going to be and the known magnitude of this. Well, actually, we know that that right there is also 25 degrees, right? So now we'd be able to find what this interior angle is going to be. It's just 15 degrees. So now we know the magnitude of this and the magnitude of that. So, and we know this angle in between of 15 degrees, right? So if we have a length and then the angle that's in between them, we could use the law of cosines to be able to solve for the magnitude of this guy right here. And quite often we will ask for the magnitude and direction of this. And if I were to do that, let me see. I'm going to take a risk and let's see if I can get this correct. We would take the square root of 2.84 squared. I wish I had the extra sig fig, but let's see. We'll keep it in there. I'm not going to recalculate it. And 4.18 squared. And I were to find that. So we go to the handy dandy Hewlett Packard calculator. Turn it on. 2.84 and take it squared. Where'd you go squared? There you go squared. And 4.18 squared. Boom. Square root. And we have 5.054 meters per second. But now let's instead take the law of cosines, right? So just remember the law of cosines says something to the effect that like c squared is equal to a squared plus b squared minus 2ab times the cosine of capital C, where capital C is the angle that's opposite from lowercase c, right? So you can try to remember this right here. So what we have for this, right, is we could say that VA with respect to B is going to be equal to the square root, that's going to be the magnitude of that, is going to be the square root of, let's say, 25 squared plus 10 squared minus 2 times 25 times 10 times the cosine of 15 degrees. And I'm really taking a chance here because I don't know for sure that I didn't mess something up along the way. So 25 squared. 25 squared. Should like try to teach the kilopack calculator usage here. 10 squared plus, and then 25 2 times 10 times, right? And then 15 cosine times that, and if I subtract that out and I take the square root, I messed it up. Which actually kind of makes sense. 1 second. Let me fix this. Pause it. Okay, I see what I did wrong. I don't know where that 25 came from. Where did that 25 come from? I don't know. And I did that up. I did that with the length of this here too, right? That was 25. I don't know why. I guess I saw 25 degrees and I thought 25 magnitude. So the triangle I drew wasn't exactly correct. Wasn't proportional. It should have been 14. 14 right up here. So I'm not going to record this. By the way, I think this might be in my video for my book, right? The Engineering Dynamics Course Companion, because I do have this example in my book right there, where you can see how you could do this by vector triangles right in there, and that when you were done, you would end up with this law of cosine right here, where you see that that's 14 right here, and there's the cosine of 15, and you end up with the same answer. But let's do it ourselves, and then if you're, I make mistakes all the time, so it's not the end of the world to show that I'm fallible here. What I often do what I will often do is to use some other method to try to check myself. All right, so there's 10. We add it, and then we go 2, 14 times 10 times 15 cosine times, and then we subtract. We take the square root, and sure enough, we get the 5.054 meters per second. So we get the same thing. Now, another way that I could approach it for the vector stuff to try to save some face here. Let me use a little AutoCAD action going on. Okay, so I'm going to start him at the origin, so it goes 0, 0, right? And I will, I have a number of things I can do. I'm going to take orthogonal right here, right there. And I will, alright, so I have my own way of doing drafting stuff. This isn't going to be pretty. I'm going to offset 14 right there. Boom. Okay. I can just drag him over. This is really cheating. And then I'm going to rotate him. Which direction am I going to rotate? I'm going to rotate him 25, but I think it's clockwise, so I'm going to go negative 25. Is that right? Yep. Okay, I got it right. All right, so this is the first vector right here. That's what Newt Dog is doing. Now I'm going to do the same thing here, and I'll come up horizontally, and I'm just going to delete him. Boom. And I'm going to make this guy 10 and offset him. And I could trim it, but I'm feeling lazy. I'm just going to do that. And then I'm going to rotate him by negative 10 degrees, right? Boom. All right. So these things are proportional to each other, right? And what we can do here, oh, there you go. Actually, set it up the right way. We could just draw a line between here and here. So there is the vector that you would have, and then we can let's see. We'll take that dimension, boom, boom, and there you go. Right. So that's what the arrows would look like, and I could even give them like little arrowheads here so you could see. Let's see. I'll turn that off. I'm just going to mess around a little bit there. These are just, oh, that was terrible. Look at that. Look how awful that was. Oh, it's gonna be these snaps. Almost just swore. There you go. All right, so there's that vector hat, and then I'm not vector hat, arrow. There you go. I'm just freehanding these right there. So those are our two vectors, and then this is the relative one between them, which, of course, the arrowheads always get in the way of each other. Boom, something like that. All right, so and we could also get the angle between these two, which is also something worth reviewing. You want to find what that new angle is going to be. What we would do, well, we could just take up here, right? We could take this guy, and we got rise over run. So if we wanted to find theta, I'll put it down here. Theta is going to be the tangent of the rise over run, which I'm not going to put the negative in there. I'm just going to recognize what quadrant, when I'm done with it, it's going to come out to. So the rise is the 4.18. It's actually the dip of the thing, I guess you'd say, and 2.84, and end up with an angle of 4.18, 2.84 divided, and find the angle, and we get 55.81 degrees, and that's going to be measured from the horizontal downwards, right? Because this is negative, right? So we know what quadrant it has to be in. It has to be down in the lower quadrant. This is positive, so it has to be over to the right. This is negative, so it has to be down. So that's what the angle that we're measuring in, that 55.8 degrees. And if you were to come back up over to here, and we were to draw a horizontal line in AutoCAD, you would, where's our angle? It's going to be this side right there. So hopefully this comes out to the right thing. Oh yeah, 56, okay. And do I have my properties button up here? Yeah, I do. I can, for whatever reason, AutoCAD changes its angles, fit primary units, tolerances. There you go, precision. Boom, 55.806. Yay, you got the same thing. So there you go. The video went a little bit longer. I put a little bit more stuff into it than I probably would have during class. Relative motion. We'll do 2 more examples, 1 more example. 2 more examples.